So now we have the diesel cycle. Go ahead and open the diesel presentation. First slide just gives you some background on development of the diesel cycle. Diesel engines known as compression ignition engines. The question there, can they knock? No, they can't knock. You rely on that auto ignition, that detonation to initiate the reaction. So there's no knocking in a diesel cycle. Going forward, just some of the thermodynamics of diesel cycles. As you'll see in a minute, we'll model or emulate a diesel cycle as constant pressure heat addition. That's the ideal diesel cycle. More modern compression ignition engines could really be modeled better as dual cycle, where you have a constant volume portion and then a constant pressure portion, as you see in the graph on slide 3 on the right. Going to slide 4. Actual cycle similar to the actual Otto cycle. Intake, fuel and air, compress, actually intake air, compress that air. Then the fuel's injected a little bit before top dead center. The reaction initiates. Then we have the power stroke produces the work. Then the exhaust valve opens, push the products out, draw in new air. The ideal diesel cycle. Again, we have an ideal compression process, isentropic. We have constant pressure heat addition, and so the volume is changing. As the volume gets bigger, you would think that the pressure wants to go down. As heat's added, the temperature goes up, and so you'd think the pressure wants to go up. Those two more or less counteract each other, and the pressure stays constant through the heat addition process. Then we have more expansion, so the reaction stops, heat addition ends, and get more work out, so the temperature goes down. Then, just like the Otto cycle, we have a constant volume heat rejection process. Slide 5, you see a PV diagram. You see the constant constant entropy compression, constant pressure heat addition, isentropic expansion, constant volume heat rejection. Here we have two parameters. Let's see where we define them. So one is on the next slide, on slide 6. You see the compression ratio is the same as the Otto cycle. So volume after compression, so volume 2, it's really volume 1 over volume 2. So the volume at bottom dead center over the volume at top dead center. However, for diesel cycle, we have one more parameter that's a ratio of volumes, and that's called the cutoff ratio. So it's the volume at time 3, the volume as heat addition is ending, divided by the volume at time 2. And unlike compression ratio, which is a geometric measure of the engine, the cutoff ratio can change. It depends on when Q out occurs, so it's not something that you could physically measure. You would need to know about the cycle, about how much fuel is injected, really. The next few slides, don't worry too much about it. You see the efficiency slide. In general, the same trend. As the compression ratio goes up, the efficiency goes up. Compression ignition engines generally higher pressure ratios than Otto cycle, so generally more efficient diesel cycle compared to Otto. Also, it depends on the cutoff ratio. So if your cutoff ratio is 1, you don't have any. Well, it's the same as the Otto cycle. And then as the compression ratio goes up, it affects the efficiency. Modern compression ignition engines and dual cycles, so that's just putting the two together. Constant volume heat addition followed by constant pressure heat addition. There it is on PV and TS diagrams. in slide 10. And then we've got a example problem here. So in the next video, I'll start the problem.